The metal press descended with a sound like thunder trapped in a barrel, and when it lifted, Werner Gruner was holding the future of German equipment manufacturing. It was April 1942, and the rectangular piece of stamped steel in his hands looked nothing like a traditional component. To the veteran craftsman observing from the workshop's edge, it looked like a mistake, a cheap shortcut that would fail the moment real physical stress hit it. Gruner had spent 15 years in the metalworking industry before the global conflict found him. He understood stamping presses, sheet metal behavior, and the economics of mass production in ways that traditional armorers never needed to. When Grossfuss AG received the contract to develop a new general-purpose rapid-fire system, the specifications were clear. Maintain the MG34's reliability, reduce production time by 60%, and use materials that wouldn't compete with tank and aircraft manufacturing. The workshop in Breslau was already producing MG34s, and everyone there knew the numbers. Each receiver required 18 hours of machining on precision equipment. Each bolt needed 12 operations on 5 different machines. The barrel demanded specialized steel alloys and skilled craftsmen who understood heat treating. The equipment functioned beautifully, but the nation needed 5,000 units per month, and the manufacturing infrastructure could barely deliver 800. Gruner's first stamped receiver sat on the test bench like an accusation. It had been formed in 8 minutes from sheet steel that cost 1/3 as much as the solid metal block required for a milled receiver. The welds were visible, rough seams that ran along stress points where traditional design would demand monolithic strength. His colleagues predicted a total structural failure. The metal was too thin, the welds would crack, the tolerances were too loose to maintain accuracy. But Gruner wasn't trying to make a cheaper version of the MG34. He was trying to make something entirely different, a system that acknowledged the reality of 1942 rather than the craft traditions of 1892. The stamped receiver wasn't weaker, it distributed forces differently. Where a milled receiver concentrated stress at sharp corners and tight tolerances, the stamped design spread loads across curved surfaces and welded joints that flexed slightly under pressure, then recovered. The barrel assembly was next. Traditional designs treated the barrel as a permanent component, something that would outlast the system itself if properly maintained. Gruner's design assumed barrels were consumable, not because they wore out faster, but because treating them as expendable components meant the rest of the system could be simpler. A quick change mechanism, a simple latch that any operator could use without tools. When manufacturing can't guarantee perfect tolerances, you design for replaceability instead of permanence. If stories like this help you see how engineering quietly shaped history, tell us in the comments what surprised you so far, and stay with us for the next chapter. The meeting room at Grossfuss AG headquarters smelled of machine oil and anxiety. It was June 1942, and Werner Gruner stood before a collection of procurement officers who had seen his initial prototypes and remained unconvinced. The MG34 had been in service for 8 years. It worked. Why risk an unproven design when the existing system already exceeded every performance specification? Gruner had prepared for this resistance. He'd brought production spreadsheets, not performance data. The question wasn't whether the MG42 functioned better, it was whether the country could build enough units to matter. The current production rate of 800 MG34s per month required skilled machinists who were increasingly being diverted to aircraft production, tank manufacturing, and the dozens of other precision industries that modern mechanized struggle demanded. He spread the numbers across the table. One MG34 consumed 48 hours of skilled machinist time. The stamped MG42 required 15 hours total, with only 6 hours demanding genuine skill. The rest was assembly work that could be performed by workers with minimal training. More critically, the MG42 used metals that weren't competing with higher priority systems. Sheet steel instead of forged blocks, standardized springs instead of custom tensioned components, pins and rivets instead of threaded fasteners that demanded precision threading equipment. The objections came fast. The hardware looked cheap. The stamped metal had visible tooling marks. The welds weren't polished. How could operators trust a system that appeared thrown together? Gruner's response was blunt. People wouldn't trust it until it worked. And it would work because every design decision was made with manufacturing reality in mind, not appearance. The roller-delayed blowback mechanism was where Gruner's industrial background became most visible. Traditional rapid-fire systems used complex locking systems, rotating bolts, tilting blocks, mechanisms that required precise machining and careful assembly. The roller system was different. Two cylindrical rollers sat in slots in the bolt, pressed outward by a wedge-shaped piece. When the system was engaged, the rollers locked the bolt in place by wedging against the receiver walls. As pressure decreased, the wedge withdrew, the rollers collapsed inward, and the bolt cycled. This wasn't simpler because it had fewer parts. It had roughly the same number as competing designs. It was simpler because it worked on principles that stamped metal could accommodate. The receiver walls didn't need to be precisely machined. They just needed to be consistent. The rollers didn't require exotic materials. They just needed to be harder than the surfaces they rolled against. The wedge angle determined the delay timing, and changing that angle was a matter of swapping one stamped part for another during assembly. The officers remained skeptical, but Gruner had one advantage: desperation. By mid-1942, the nation was committed to a massive struggle that consumed material faster than traditional manufacturing could replace it. The choice wasn't between the MG34 and the MG42. It was between the MG42 and not having enough equipment at all. The test range outside Breslau was silent except for wind moving through grass. Werner Gruner watched as technicians loaded the first production specification MG42 with a belt of 7.92mm ammunition. This wasn't a demonstration of impact, it was a systems test. Every component in the hardware represented a hypothesis about how stamped metal and roller mechanics could work together, and the next 60 seconds would validate or destroy months of design work. The fundamental challenge of any automatic system is managing energy. Each cartridge contains enormous force compressed into a tiny space, and when ignited, that force has to accomplish several tasks simultaneously: propel a projectile, cycle the mechanism, contain pressure, and dissipate heat. Traditional designs handled these requirements through mass and precision. Heavy components machined to tight tolerances that absorbed and channeled forces through carefully designed pathways. Gruner's approach inverted the logic. Instead of building components strong enough to contain forces, he designed a system that redirected forces before they became destructive. The roller-delayed blowback was the key. When a round was triggered, the pressure pushed the bolt backward, but the rollers were wedged outward, creating mechanical resistance. This delay was precisely calibrated, long enough for the projectile to exit the barrel and pressure to drop, but short enough that the mechanism cycled completely before the next round needed to chamber. The genius wasn't in the delay itself. Delayed blowback had existed for decades. The genius was in implementing it with components that could be stamped, welded and assembled without precision machining. The receiver walls that the rollers locked against didn't need to be precisely flat. They needed to be consistently curved. The rollers didn't need exotic metallurgy. They needed surface hardness. The wedge didn't need complex geometry. It needed the correct angle. When the mechanism was engaged, the system responded with a sound that shocked everyone on the range. Not the sharp, rhythmic crack of the MG34, but a continuous roar, so rapid that individual sounds merged into a sustained tone. The rate of operation was nearly 1/200 rounds per minute, roughly double the MG34's output. But this wasn't a design goal, it was a consequence of efficiency. The faster cycling meant each component spent less time under peak stress. The bolt moved backward, ejected the spent casing, stripped a new round from the belt, chambered it, and locked. All in the time it took competing designs to complete half that sequence. This speed was possible because the roller mechanism had fewer moving parts and simpler motions than rotating bolt designs. Simplicity enabled speed, and speed enabled lighter components, which further enabled speed in a feedback loop that pushed the system to its practical mechanical limits. The barrel change mechanism demonstrated the same systems thinking. Traditional designs treated barrel changes as maintenance procedures, complex operations performed by specialists with specialized tools during extended breaks. Gruner's design assumed barrel changes would happen frequently and needed to be simple enough for anyone to perform under stress. A latch, a twist, a pull. The hot barrel came free, a cool one slid into place, the latch closed. 8 seconds, no tools, no precision alignment required. This was possible because the barrel wasn't precisely fitted to the receiver, it was consistently fitted. The tolerances were loose enough that any barrel would fit any receiver, which meant mass production could build parts in different facilities and assemble them anywhere. Interchangeability wasn't a luxury, it was the foundation of the entire system. Do you think this design choice was inevitable or a risky gamble at the time? Share your view in the comments and pass this story to someone who enjoys understanding how things really work. The endurance trials began in August 1942, and they were designed to break things. Werner Gruner stood in the Kummersdorf proving grounds, watching as technicians subjected his design to conditions that no equipment would experience in normal use. The goal wasn't to prove the MG42 worked. The goal was to find exactly where and how it failed, then redesign those failure points before production scaled. The first test was thermal. Rapid-fire systems generate extraordinary heat. Each ignition produces temperatures exceeding 3,000 degrees Fahrenheit in the chamber, and sustained use concentrates that heat in a small space. Traditional designs used heavy barrels and tight tolerances to manage thermal expansion. Gruner's stamped receiver and lighter barrel responded differently to heat, and the question was whether those differences would be catastrophic. They operated the system for 5,000 rounds in sustained bursts, changing barrels every 250 rounds. The stamped receiver heated unevenly, expanding in ways that precision machine components wouldn't, but the loose tolerances absorbed that expansion. Where a tight-fitted mechanism might bind or jam as metal expanded, the MG42's components simply took up the available slack. The system kept functioning. The second test targeted the roller mechanism under extreme conditions. They deliberately fouled the system with sand, mud, and carbon buildup, then operated it until something failed. The failures came, but they were predictable and recoverable. The rollers occasionally stuck when contaminated, but a simple pull on the charging handle cleared them. The extractor sometimes slipped on badly fouled casings, but the system was designed so that a failure to extract didn't prevent the next round from chambering. The stuck casing simply ejected when the next round pushed it clear. This resilience wasn't accidental. Gruner had designed for graceful degradation rather than perfect performance. A precision mechanism either works perfectly or fails completely. A system with built-in slack can absorb contamination, wear, and damage while continuing to function at reduced efficiency. The MG42 didn't demand perfection from its environment. It adapted to imperfection. The barrel change mechanism underwent particular scrutiny. The concern was that repeated changes under field conditions would deform the quick-release mechanism or misalign the barrel interface. The testers changed barrels 500 times, deliberately rough-handling the components. The latch showed wear, but it didn't fail. More importantly, accuracy testing after 500 barrel changes showed no degradation. The barrel seated consistently because the interface was designed for consistency, not precision. The most revealing test was comparative. They brought in an MG34 and subjected it to identical treatment. The MG34 performed flawlessly in clean conditions with proper maintenance. But it was sensitive to contamination, thermal stress, and rough handling in ways the MG42 wasn't. The MG34 was a precision instrument that demanded precision conditions. The MG42 was an industrial tool that assumed nothing would be perfect. By September, the data was clear. The MG42 would fail in specific, predictable ways under extreme abuse, but it would continue functioning under conditions that would disable more sophisticated hardware. The stamped receiver wasn't weaker, it was more forgiving. The roller mechanism wasn't less reliable, it was more tolerant. The loose tolerances weren't a compromise, they were an adaptation to manufacturing and operational reality. Winter 1942 brought the answer to a question Werner Gruner hadn't known he was asking. Why did the system work when every traditional principle suggested it shouldn't? The revelation came not in the workshop, but in the production data from 3 different manufacturing facilities that had begun MG42 assembly. The first facility used precision stamping equipment and skilled metal workers, conditions similar to the original Breslau workshop. The second used older, less precise presses and workers with minimal specialized experience. The third was a repurposed automotive plant with equipment never designed for creating such hardware. Traditional logic said the first facility would produce superior units, the second acceptable ones, and the third would struggle. The reliability testing showed something unexpected. All 3 facilities produced systems with statistically identical performance. The MG42s from the automotive plant, made on repurposed body stamping equipment by workers who'd been building trucks 6 months earlier, functioned just as reliably as units from the precision facility. Some showed better finish, some had tighter tolerances, but all of them worked the same way. This was the final curiosity, the reason Gruner's system succeeded where conventional approaches would have failed. He hadn't designed a system that required perfect execution. He'd designed a system that tolerated imperfect execution while maintaining consistent performance. The roller mechanism worked because the physics didn't depend on precision, it depended on proportion. As long as the roller diameter and wedge angle maintained the correct relationship, the actual dimensions could vary within a surprisingly wide range. The stamped receiver revealed the same principle. The thickness of the metal mattered less than its consistency. The exact placement of welds mattered less than their quality. The receiver from the automotive plant wasn't built the same way as the receiver from the precision facility, but both receivers did the same job because Gruner had designed for functional equivalence rather than dimensional identity. This insight represented a fundamental shift in how complex mechanical systems could be conceived. Traditional engineering assumed that performance required precision, and precision required skilled craftsmanship or expensive tooling. Gruner demonstrated that performance could also emerge from systems designed around principles rather than specifications, where the relationships between components mattered more than the absolute qualities of individual parts. The barrel interface exemplified this thinking. A precision-fitted barrel requires both the barrel and receiver to be machined to tight tolerances, matched during assembly, and maintained carefully thereafter. Gruner's quick-change system worked because the interface was designed around a simple principle. The barrel needs to be held in consistent relationship to the chamber, with a seal maintained at the breech. This could be accomplished with a spring-loaded collar and a mechanical latch. Components that could be stamped required no precision fitting and worked regardless of which barrel was paired with which receiver. The feed mechanism operated on similar logic. Traditional belt-fed systems used complex arrangements that required careful timing and adjustment. The MG42's feed mechanism was essentially a lever and a slide. The bolt movement directly drove belt advancement through purely mechanical linkage. It couldn't get out of time because there was no timing to maintain. It was self-synchronizing by design. This was the secret hidden in stamped metal and roller locks, systems designed around physical principles instead of craft traditions, could achieve reliability through different means. Not through precision, but through proportion. Not through tight tolerances, but through correct relationships. Not through perfect components, but through forgiveness built into how components interacted. The hardware that looked crude and unfinished worked consistently because it was honestly designed for the real conditions of production: inconsistent materials, varying skill levels, repurposed equipment, and the absolute necessity of interchangeable parts produced by facilities that might never coordinate directly. The MG42 entered full production in late 1942, and by the end of the conflict, over 400,000 units had been produced, a number impossible to achieve with traditional manufacturing methods. But the system's impact extended far beyond those production figures. Werner Gruner had demonstrated something that would reshape how humans designed complex mechanical systems for the next 8 decades. The post-event analysis revealed the depth of his innovation. When engineers from other nations examined captured MG42s, they initially dismissed the design as a desperation measure, crude stamping and simplified mechanisms that sacrifice quality for quantity. But detailed testing showed that reliability rates matched or exceeded traditionally manufactured hardware. The MG42's mean cycles between failures was higher than the MG34, despite using cheaper materials and less skilled labor. This forced a reconsideration of fundamental assumptions. What if precision wasn't the only path to reliability? What if tolerance of variation could be designed into systems rather than eliminated through manufacturing control? What if the measure of good engineering wasn't how perfectly components were made, but how consistently they interacted? Various post-1945 systems, including several standard NATO designs, all borrowed from Gruner's principles. Not just the roller delay mechanism or stamped receivers, but the deeper insight: design for the manufacturing reality you have, not the ideal conditions you wish for. Build systems that tolerate variation rather than demanding perfection. Make interchangeability the foundation, not the final achievement. The quick-change barrel became an industry standard, not because components needed changing more often, but because designing for easy replacement meant designing the entire system around a modular interface. And modular interfaces enabled easier manufacturing, maintenance, and field repair. The principle extended beyond this specific hardware to automotive engineering, aerospace systems, and industrial machinery. Design components as systems, not as collections of parts. But perhaps the most profound legacy was philosophical. Gruner demonstrated that constraint could drive innovation more effectively than abundant resources. He didn't have the luxury of precision machining, exotic materials, or unlimited skilled labor, and those limitations forced him to think differently about how machines could work. The absence of traditional tools meant he couldn't rely on traditional solutions. The MG42 wasn't successful because it was better at its intended function in a vacuum. Many would argue the MG34 was a superior piece of craftsmanship in pure performance terms. It was successful because it was honest about what could be built, by whom, and under what conditions. That honesty forced innovations that outlasted the conflict that prompted them. By the 1950s, Gruner's principles had become so thoroughly integrated into mechanical engineering practice that new generations of engineers learned them without knowing their origin. The idea of designing for manufacturing tolerances, building in graceful degradation, creating systems that worked through proportion rather than precision. These became common knowledge, the obvious way to approach complex mechanical problems. Yet the MG42 itself remained the purest expression of these principles. Every component existed because the system required it. Every tolerance was as loose as physics permitted. Every interface was designed for consistency rather than precision. It was a tool of its time, yes, but more fundamentally, it was a proof of concept. Evidence that human ingenuity could find different paths to reliability, different approaches to complexity, and different relationships between design and manufacture. Werner Gruner returned to civilian metalworking after the period of unrest, largely anonymous, despite having created one of the most influential mechanical systems of the 20th century. His name appears in technical histories, but his deeper contribution, the demonstration that systems thinking could replace craft thinking in complex mechanical design, became so fundamental to engineering practice that it no longer needed attribution. The system he built from stamped metal and roller locks outlived its original purpose and became a template for how humans could design anything that needed to work reliably under imperfect conditions, which it turns out describes nearly everything worth building. If you enjoy calm, true stories about how engineering shaped the world, subscribe to the channel, leave a like, and tell us from which country you're watching.